Okay, so last week I introduced to you guys two main topics. The first topic was we want to talk about new types of functions. You guys should hopefully recognize linear functions, nice straight lines, and quadratics. Our goal now is to do so many more. And so, for example, we just did an example where this is a cubic. Makes sense? Or this right here, you know, I want to take a stab at what this kind of graph might have been. Probably x to the 6. Yeah, that seems likely. You can tell this for a couple of reasons. One, it kind of looks like a quadratic. I know it's not a quadratic because a quadratic would look just like this. But you know how it starts in the bottom and ends in the bottom? That should give away that it's something to the power of either 2, 4, 6, 8, 10. That makes sense? It's got to be an even. And then to figure out what it would be, try to maybe figure out how many little twists there are. So like there's 1 twist, 2 twists, 3, 4, 5. So that probably means it's a 6. So far, so good. So we talked one day about just introducing the idea of higher order polynomials. And then the second day we talked about how to combine functions by doing things like adding, subtracting, multiplying, and dividing them. And so this was that notation. You could take two graphs and add them, subtract them, multiply them, and divide them. So I had something that I originally would have done to start classes warm-up questions, but I don't want to take all day on it. So why don't we just work on B here and just focus on like a table of values, because otherwise this is going to take forever. Let's say I were to ask you to, like, say, add functions. So like if I were to make a new column here, maybe I were to ask you to do f plus g of x and kind of make like a new row right here. This is actually really similar to one of the questions on your assignment. Here's how you might go about solving it. Find an input. I don't care what the input is, but find me an input. So why don't I start with -4? That's the first one on there. Well, if you plug in -4, I don't know what the graph looks like, but I know that -4 gives an answer of -3 for one of the graphs, and it gives an answer of 1 for the other graph. Well, if I want to add those graphs together, that would have been -2. How did I get that value? Well, I basically took those two things and added them together. So what about for the next one, -3? Well, it would be -2 and 0. So actually, it's still -2. Actually, for this one right here, I'm starting to notice a pattern here. This is also -2. I think based on how these graphs work out, it's actually -2 all the way along. Does that make sense? So one of the ways you could write it then is your answer could be -4 with -2. And then there could have been a -3 with a -2. And a -2 with a -2. Like you could write it in coordinate pairs. This is what f plus g of x is. Those are some of the points on the graph. Does that make sense? Let's just do one more here. Let's look at this graph right here. And let's try to draw what it would be if we were subtracting the two graphs. Actually, no, let's multiply them. Let's see what multiply looks like. So pick an input for x. I'm going to start right here at 0. Here and here are when x are 0. So one of them is -1 and one of them is 3. So if you take the -1 and then the 3 and times them together, you'd get a -3. So there's a point on my graph. Then find a new value for x. So how about 1? Here it looks like it's 2.5. And there it looks like it's -4. That makes sense? So here my output of 2.5 times by my output of -4 should give me -10. Wherever that is, way down here. That would be 1 with a -10. This one would have been 0 with -3. Let's just do one more. Here we've got 2 and okay, so that's what, -5 and 1. So -5 times 1 would actually be at -5, I guess. So 2 would have given you -5. Does this kind of make sense what I'm doing? Ultimately, we're going to get a new graph. I don't know fully what the new graph is going to look like. We can do this point by point. It would take us forever. But those are kind of the skills we want to work on. So far, so good? Okay. I want to go back to last day's notes and just cover one thing that I felt like I skipped over a little bit. The hardest one by far is dividing. Multiplying, adding, subtracting, most people are really fine with that. But if you have last day's notes, or even if you don't, I don't need you to do a lot with them, but I just want to point out two graphs that we were going to do. One of them was going to be this one right here, x squared plus 9x plus 14 and x plus 2. I just want to graph them on our calculator. So you can just watch if you want. So if I want to graph these on the calculator, just make sure you get them in the right order, because it totally makes a difference whether you do 1 over 2 or 2 over 1. So I'm going to take this first function up here. So that'll be bracket x squared plus 9x plus 14. And I'm going to divide it by the x plus 2. Divided by x plus 2. This is what that looks like. Let me know if you can't get that to work in your graphing calculator. We just took a quadratic and divided it by a linear. What kind of graph does this look like? Yeah, it looks linear, doesn't it? And it is actually basically linear, and there's a reason why. I want to try to prove that to you just with a quick factor here. You know how you have, like, say, x squared plus 9x plus 14? You guys remember how you can factor by looking for numbers that add to give, say, 9 and multiplying to give 14? Anybody know what numbers add to give 9 and multiply to give 14? That'll do it, yeah. So if you go x plus 2 and x plus 7, that's what that thing right there equals. And let's say you're supposed to divide it by x plus 2, because that's what our graph was supposed to be, f over g. What's going to happen if you have an x plus 2 on the top and an x plus 2 on the bottom? Cancel, wouldn't they, right? And so in canceling, what are you left with? Well, you're left with x plus 7. What is x plus 7? Well, it's linear. Hence, see how this graph right here is linear? However, what I didn't do last day was then there was another one 2 slides after it. It's almost the exact same thing, only now it was x squared plus 9x plus 8 and x plus 2. So I'll just rewrite that here. X squared plus 9x plus 8. This guy right here can also be factored. You're looking for numbers that add to give 9 and multiply to give 8. What adds to give 9 and multiplies to give 8? 1 and 8. 1 and 8, yeah. So if you factor this, it would be x plus 1, x plus 8. And that would all be over x plus 2. Here's the reason why I want to just point out this issue here. You know how in the last example, stuff could cancel? On this example, can things cancel? No. So what I want to do is I want to just go over here and just make a quick subtle change. And rather than make this a 14, make this an 8. And now look at the graph. Is it linear? Not at all. And all it took was changing one number to make it that it doesn't... I mean, it's still factored, actually. But it didn't factor and cancel. So here's the terms I need you guys to know. On a graph like this, there's a vertical line drawn on mine, which I know you guys probably don't have it drawn on yours. But we have a name for that vertical line. It's called an asymptote. You guys recall that? There could be an asymptote in a dividing graph. However, if I go back and do the first one, which was like plus a 14, so this is the one that looked linear again. You're not going to get an asymptote, but there is kind of a weird anomaly to this graph I need you to point out. If you go to your table of values and don't have it start at 10,000, start it at 0. See how the table of values looks fairly straightforward? 0 gives 7, 1 gives 8, 2 gives 9, 3 gives 10. There's actually going to be something odd about this graph right here at -2. You see how right here on the bottom of the fraction right here, the factor is x plus 2. That means the root would be minus 2. You can't plug a minus 2 in right here, because if you try to, you'd be dividing by 0. So this creates something weird. We call it a hole in the graph. And I have a slide for that somewhere. Right here. Literally what there is there is a hole in the graph. You'll never see this hole, because this hole is infinitely small. Okay. 2.00001 is still a number that can be used. 1.99999 is still a number that can be used. But if you tried to use 2 right on the dot, you can't, because that means you'd be dividing by 0. So if I were, say, to go to my table here, do you know how you can do like a value? Let's see if I can make this work. Calculator keeps freezing today. Value. You know how you can like type in a number to solve for a value of? So if I were to plug in 3, sure, 3 gives me 10. It should, right? If I try a value and I go 2.01, it will give me a spot for that. But if you try to do a value at exactly 2, like right on the dot, why did it give me 9? Oh, thank you. So I can calculate the value of -2. Then it should actually like literally leave it blank right there. And so on my graph right here at -2, there is a hole. But like, you know how like pixels are like so big for your graph here? If you were to zoom in and keep zooming in, you'd never actually see that hole. So what we often do is we draw it on a graph by just drawing a little circle right there, just to let you know that there is a hole in the graph. Does that make sense? So 2 weird anomalies that happens when you divide. Okay? Anomaly number 1. If you're dividing 2 functions and they factor and something cancels, usually it's going to make a graph that doesn't look weird anymore, which is kind of nice. It's going to make a nice linear graph again. The only problem is there's probably a hole in that graph. And you won't see it on your calculator because it'll just look linear. So the advice I'd give you is go to your table and just see whether there's like an error there. Does that make sense? The other possibility for a dividing graph is that it does not factor and cancel. Like it might factor, because like this guy right here does factor, but it doesn't cancel. Does that make sense? When we wrote this one out right here, there was an x plus 1, an x plus 8, and an x plus 2. Nothing cancels. In this example here, there'll be that asymptote then when you graph this thing. And it'll look very like a strange graph. If you go to your table, -2 still won't work, but it's for a different reason. Does that make sense? All right, cool. I just wanted to point that out because I didn't cover that all that well last day, or actually at all. It's not much, it's just knowing the difference there. Okay, let's keep moving on here. What I'd like to do then is talk about something called a composite function. This is the last thing we're going to do for like this kind of assignment set. If I were to ask you what a function is, maybe something that would come to mind is like an equation. I like the analogy of a machine. So I'm going to go back to that machine analogy. If you give me $3, I will give you a bag of chips. Does that make sense? That's an equation. If you give me $6, I'll give you 2 bags of chips. Does that work? So for example, here's a function. This function works by squaring whatever you give me. So if you give me $3, I will then square it and give you back 9. Does that make sense? Or here's a function. What this function means is that you always add one more dollar to it. So if I give you $9 and you add one more, you get 10. What we're now going to do is as a mechanism where we take one function and we get an answer, and we immediately take that and plug it into a second machine. So here's my analogy. You guys get my vending machine analogy. I have American money though, and American money doesn't work in a Canadian vending machine. So what I have to do is I have to take my American money, put it into one of those machines that converts it into Canadian money, and then as soon as I get my Canadian money, then I take it to the vending machine and buy my bag of chips. Does that analogy make sense? That's what's happening here. First, we're going to plug in 3. 3 is going to get squared and give us 9. But immediately, we're going to take that 9 and plug it into another machine and add one more to it to get 10. And so what you might say then is that the point 3, 10, is on this graph. You originally plugged in a 3. 3 turned into 9. 9 turned into 10. So therefore, from start to finish, we started with a 3 and we ended with a 10. So really all we're doing is we're just doubling up on this. Does that make sense? Got lots of pictures to show you here. The way we write this looks something like this. You go f bracket g bracket x. What you really want to do is kind of start from like the inside out. So ignore the fact that there's an f right here just for a second. What does g of x mean? Well, g of x means let's plug something into the g equation. Does that make sense? Let's say you do that and you get an answer. Well, then what you need to do is then plug that answer into the f of x equation. Oh my goodness, I can't find an eraser here. Let me try that again. So what this notation right here means, plug a number into the g equation, get an answer. But as soon as you're done that, immediately plug that into the f equation. So here's how this might look then with an equation. I'm just going to make some more room here. What was it? It was 3x plus 4. And then the other question was 5x minus 6. Okay, so here's my equations. And I'm going to ask you to do f bracket g bracket x. So let's start with the g of x equation. What is my g of x equation? It's this guy right here, 5x minus 6. So I'm just going to write that out here. When I'm done with that, I'm going to plug that into the f of x equation. What is the f of x equation? Well, the f of x equation is take 3 times an answer and add 4. But my answer would have been whatever this thing here would have been. So it's going to look something like this. 3 of that plus 4. It's like something inside of something else. Here is an equation, 3 times something plus 4. But that something, which I called x, is actually really this equation right here. Kind of what we're doing is we're taking the g of x equation right here, and you guys know how to do substitution? Remember that from last year? That's kind of what this is. This is like a substitution. We're substituting this equation inside right there. So if I were to give you a number for x then, let's just try this. If I were to give you f of g of 2, here's how this might look. You'd plug a 2 in right here. So like 5 times 2 would give you 10. Minus 6 would give you 4. And then instantly you'd take that 4 and you'd then plug it into the other equation, which would be 3 times 4 plus 4. So that one more time. So if I were to give you f of g of 2, the first thing you do is you find g of 2. So g of 2 means 5 times 2 minus 6. That would have been 4. And as soon as you get that 4, you plug that 4 in for x there. So all of this mess right here is 4. 3 times 4 is 12. Plus 4 more is 16. So therefore, a point on this graph would be 2 and 16. You able to follow that? Yeah. Okay. Okay, so that's a notation thing basically. What this means here then is like start with x. So that's an input. What I want you to do is take your input and put it through the G vending machine. And as soon as you're done, yes. Because what the opposite of that would be G bracket F bracket X. If I were to write it and then get that answer and then put it into the G of X. Does that work? Yeah. So like analogy would be like this one right here means take your American money, plug it into the American money converting to Canadian money machine. Once you have Canadian money, then put it into the normal vending machine. Whereas this right here means take your American money, try plugging it into the vending machine, and then after you're done, then try to convert that into Canadian money. And so like sometimes one way makes more sense than the other way. That makes sense. So like order definitely matters as to which one is which. Here's a picture that I thought maybe kind of helps make sense. if you write it like, oh, by the way, f bracket g bracket x is the same thing as writing f open circle g. Yeah, not a dot. A dot means multiply. An open circle means the same thing as this. Yeah. So maybe this diagram helps make sense. You're going to take apples and you're going to turn them into lemons. But then immediately you're going to take lemons and turn them into oranges. So at the end of the day, what you really have done is gone lemons to apples to oranges. Like this is your x value, and this is your y value when you're done. But we had like an intermediary step. So let me do some examples. Sometimes if I just example you to death on this, kids will find that it helps click. So let me walk you through this. Let's try to find what f bracket gx is going to be. So my recommendation here, let's start in the middle. Okay. The first thing we have to do is find the g of x equation. So I'm just going to write that out. It's x plus 6. That's the gx equation. That is now going to get substituted into the f equation. So you see how the f equation is 4x? It's going to be 4 of my x plus 6. See how that works? So if you read this from like left to right then, f of g of x means start with f, which is 4x. But we're not actually going to use x, we're going to use gx's. So I start with my 4, but rather than writing x, I write whatever g of x is, which was x plus 6. And if I wanted to, I guess I could make this 4x plus 24. That is what this equation is. It's a long form of substitution. Yeah. What I really want to work with you guys on then is the notation, because that's probably what throws most kids off right away. So let's try this one, g of h of x. So I might suggest start in the middle. Find me the h of x equation, which is x squared. Now find the g equation, but everywhere that you used to write x in the g equation, write x squared. So the g equation was supposed to be x plus 6, so now it'll be x squared plus 6. That's what that equation is.
Why don't you like replace like the x, because it was already an x there?
Okay, so see how in this one right here, there's still an x still sitting right here? I'm not going to replace x. However, see this one right here, how there's no longer an x there? When I'm done on this one right here, I'm then going to replace x with the number 4. I hope that answers your question here. On this one right here, you should still have x's. On this one right here, you should still have x's. But on this one right here, when you're done, we're actually going to make x become 4, and we're actually going to get a number. So let's start with f of 4. Let's ignore the 4. Let's just go with f. F's equation is 4x. So I'm just going to write 4x for right now. 4x. And then what h says to do, h says to do x squared. So it doesn't mean that make this x squared. It means that all of that is now squared. See how that works? H means to square something, but that something that you're squaring is actually that thing inside. But I'm not done now. Now I'm going to replace my x with 4. So what I actually have is 4 times 4 squared. So 4 times 4 is 16. 16 squared, I think, is 256. Is it? Or did I do that wrong? 256? Okay. So let's try the next one here. H of x. So start with h of x. That's x squared. So that's kind of like what this little bit right here is. That's x squared. And then I'm told to do h of that. So that means to do x squared a second time. So it's kind of like you have an x squared inside another x squared. So it'll kind of look like this. Like that. Here is a something squared. And then inside of a something squared is another something squared.
Isn't that the same as just writing another x squared on the outside? Like, would that make it kind of the same, or am I wrong?
you would end up getting, yeah, like you could then write this as x squared times x squared.
Right, that's why I was confused.
Yeah. And so you could actually call this x to the 4 if you wanted to. Okay, what's different about e then? Okay, so when we're done, make sure that we don't just leave x's there, but that we actually plug in a number. So I might recommend, let's start with f. So f's equation is 4x. And then around that 4x, I want to put that 4x inside of the g of x function. So the g of x function is supposed to be x plus 6. So it'll be 4x plus 6. Makes sense? So like maybe looking at it now from left to right, the g function means you should have something plus 6. And I have a something plus 6. But what is that something? I'm using fingers here. Well, that something was supposed to be the f function. So that's why I have the 4x plus 6. But again, I still have another x. That x is now no longer going to be x. It's now going to be negative 3. So 4 times negative 3 plus 6 is negative 6. Okay, let's go crazy then. Take it slow, work your way from the back. What is f of x? Okay, so I'll start by writing 4x. Around that, I'm now going to write the g equation. So the g equation is supposed to be x plus 6. Perfect, so I'm just adding a plus 6. The 4x is taking the place of the x. Around that is the h equation. So the h equation is to take all of that and make it x squared. So it's that squared. Then I have the f equation again, which is supposed to be 4 of that. So remember, this is now what x is, so we just need 4 of those. Now, this is what x is. Yes, it's really, this is more reasoning than math. Right? Like the math skills here are not really lots of adding, subtracting so much as just, can you fit the puzzle together? Then the last step is to do g of all of that. So this essentially is the all of that. So it was supposed to be x plus 6, so really this is the x. So we just need a plus 6. That's what it's equal to. We could FOIL it, but let's not. I mean, we could. Hopefully you guys know how, but that's not purposeful right now. So let me walk it through now from left to right, see if this makes sense. First, you're supposed to have a g equation. A g equation is supposed to be a something plus 6. Do I have a something plus 6? Sure. This is the something, and I'm adding 6 to it. Does that work? Then I'm supposed to have an f equation. The f equation means I'm supposed to do 4 times something. Yep, here's a 4. This is now the something. Then I'm supposed to do an h equation. The h equation says you're supposed to do something squared. Yep, this guy right here is the something that got squared. Then you have to do the g equation again, which is a something plus 6. So here is a something adding to 6. And then lastly, you're supposed to do an f equation, which is supposed to be 4 of something, and that's actually what I have circled right here. The only step that could be left is if I actually give you a number to put right here, you could actually plug that number in. So far, so good? Okay. Okay, I need you guys to know just the different notation and ways that we read this then. Okay. If you guys get the concept, which is basically, this is a fancy way of doing substitution. Here's how you read this. F bracket gx is read as f of g of x. So it means like, take a function of g of x. Or working backwards, take x, plug it into g, plug it into f. Okay. And you could write it either like this or like this. That open circle is another valid way of writing it. Okay. I got to point this out here. Composition of functions is not multiplication. F open circle g of x is different than f next to g of x. This means take your two y values and multiply them. This right here means take one and plug it inside the other one. You guys know those Russian nesting dolls where there's like a doll and you open it up, there's another doll inside and you can keep doing that for forever? That's kind of what I like for an analogy of this. What I just did right here was like a doll inside another one, inside another one, inside another one, inside another one. Does that make sense? So, but that's different than taking them and multiplying them together. So let's try another example then. You guys want to try this one by yourselves, see whether you have the concept? I'll give you just a second to try it. The only twist here that I've given you is that I've given you some really ugly looking functions. But it doesn't change the basic principles. So maybe start by looking at this notation. What does this notation here, what is it asking you to do? What is G open circle Fx? It means this. G F. So it means take the f function and plug it inside the g function. So like substitute the f1 inside the g1. So it'll look like this. You'll have negative x to the minus 1 squared. That's what it would be. Fantastic. Yeah.
So can you write it like that? Is that okay?
Nope, because what you've done here is the multiply one. You've taken one of them and multiplied it by the other
Okay,
one.
so
You haven't
we
actually
don't
put it
put the
inside
X
the other
there.
one.
Oh, okay, that makes sense. Got it.
Okay.
What did it start with then? Because like, the f of x equals like x into the negative one.
Yeah.
Uh,
Do you guys remember what f to the negative 1 means from last year? Nope.
negative.
No. X to the negative 1 means 1 over x. It's a reciprocal graph. Another way of writing this would have been to go negative 1 over x squared. Do you guys remember that at all? X to the negative 1 means 1 over x. X to the negative 2 means 1 over x squared. X to the negative 3 means 1 over x to the 3. Does that ring a bell? So this is what your equation basically refers to then. Okay, let's answer my question then. I didn't actually ask you just to get me the equation. I asked you to get me the domain. What does domain mean? X values, yeah. Basically, I'm asking you what x values can you plug in? Can you plug in 5 for x? I don't see any reason why not. 1 over 5 is a number. I can square that number and make it negative. That certainly should work. But there's one value I can't use. 0, yeah. Yeah, so you might write it like this then. Your domain would be x is an element of the reals, but maybe we write an exception and say x cannot be 0. That makes sense? That's the only number you can't use. Now, like, take this function right here, negative x squared. Can you plug in 0 into that function? Sure. You can take 0, square it, 0, and make it negative 0. But like because this guy right here is 1 over x, you can't use 0. Does that make sense? So even though one of the functions does work, but the other one doesn't work, does that make sense? Like if one of them it works and one of them it doesn't work, well then together it doesn't work. Let's try another example here. Let's try to go backwards and figure out what f of x and g of x would have been if I give you the answer and I ask you to work backwards. Does it seem like there is a function inside another function on this first one right here? Doesn't that kind of pop where like, see how that's in common? Like there's an x minus 2 in a bracket. There's an x minus 2 also in a bracket. Wouldn't it seem likely that like the x minus 2 has been plugged inside of a second function? So in this example here, the inside function is the x minus 2. What's the other function then? What has it been plugged into? Go ahead. Yeah. That's it, yeah. What's tricky about this one is we actually took the x minus 2 and plugged it in twice. That's okay though. That's valid. So in order to make this work, we actually took the x minus 2 function, that's the inside one here, and shoved it inside of this function. So they ended up with this thing in there twice. Okay, how about this one? Does it look like there's a function inside of something else on this one here? I don't know. Sure, there's something there. What if I were to make my g of x be the x to the third plus 1? Right? So imagine that this is what's been shoved inside there. What would the function that it got shoved into then be? Do you guys remember what these lines mean, by the way? Yeah, it's called absolute value. Well, then it would be the absolute value of x plus 2. And what we've done is we've shoved this guy inside there. Does that make sense? Okay. Okay, almost done. I'll give you guys some time to work on this now. Let's try sketching a graph. So sometimes we can give you equations to work with, sometimes we can give you points to work with. What if I give you a graph to work with? Could we sketch what this graph would look like? This is one of the most challenging things to keep track of. So what I'm going to recommend we do is let's actually make a table. And let's figure out what x is. Let's figure out what it makes g of x become. And then let's figure out what that makes, running out of room here, f of g of x become. Sorry, I'm running out of room here. Give me an x value to start with. Doesn't really matter what we start with, we just need a number. Sure, 1. Okay, so let's start with 1. So here's what this notation means. We should figure out what happens if you do g of 1. Let's start inside out. So if you do g of 1.
Mr. Baxter, please report to the office. Mr. Baxter, you needed in the office.
Right here is 1. The g graph is the red graph. So what y value do you get on this graph right here? Negative 0.5. Yeah, negative 0.5. I totally agree. Yep. Now that I have negative 0.5, now what I have to do is I have to plug that into the f equation. So the f equation is the blue line. But the question is, well, where do I look? And the answer is I look right here. See how this would be where negative 0.5 is? Now take negative 0.5 and drop it down to this equation here. Perfect.
Marley Duncan, can you please call 100? Marley Duncan, please call 100.
So a point on my graph then would be 1 with negative 2.5. Ignore the middle step. The middle step is just to kind of help keep track. But a point on my graph would be 1 with negative 2.5. So I could actually plot that here at 1 and negative 2.5. Let's try another one. Let's go 2. So find 2 as an x value, so right here. And fortunately, either way, 2 gives us an output of 0. Does that work? Okay, so now I need to go over here to where 0 is. And I have to see what 0 would give me on the f graph. And on the f graph, it would give me minus 2. So then 2, negative 2, is a point on my graph. Does that make sense? Do one more. Let's go 3. What does 3 give you on the g of x graph? On the g of x graph, 3 right here gives me a y value of positive 0.5. Immediately, I take that positive 0.5 and I re-go back to my x-axis and say, well, here's where positive 0.5 would be. What would that give me on the blue graph? Over here, it looks like it would give me negative 1.5. Does that make sense? Here's the positive 0.5 for an x value. Drop it down over here. The y value gives me negative 1.5. So that means my next point would be 3 gives me negative 1.5. Makes sense? We can keep going, but hopefully that's the point. I won't do this last slide. I want to give you guys a break and some work time. If I could give that exact same graph, would it look the same if we were to do g then fx? I would say no, it's completely different then. Here we're doing f then g then x. But on the next one, if we did G then F then X, it would be a completely different order, wouldn't it? So I won't take the time to go through doing that exercise, but order definitely matters. So here's what we've accomplished so far. So I want to pause here. We've talked about 4 operations. You can add, subtract, multiply, and divide. I would say add, subtract, multiply, those are the easiest. Okay? And you can do it either with a graph. I can give you some points. I can give you an equation, but those are usually the most straightforward ones. Divide is the trickiest. The reason why divide is tricky is because when you're going to divide things, you know, like the bottom of a fraction can't be 0. So that means one of 2 possibilities. Either it will factor and cancel, which results in a hole in the graph. Technically, the term for that was called a point of discontinuity. That's like the official term of it. But I like to call it a hole. Okay. The other possibility is that you'll have 2 things dividing each other, and it won't cancel. In that case, you'll get an asymptote, and that makes the graph look really ugly. Then the last possibility, this 5th possibility, so add, subtract, multiply, divide. The 5th possibility is you could take function 1 and literally shove it inside of function 2, like substitution. Or you could take function 2 and shove it inside of function 1. And so those we write as either g bracket fx or f bracket gx. As long as you get the concept, and I like the vending machine analogy, take your money, put your money into, like, say, a change machine. That's the first machine. Then once you get your change, put it into the next machine. That's what's happening. But if you were to try to put the vending machines in the other order, maybe it doesn't work as well. Okay. Any questions so far? Okay, go take 5. When you guys come back, start working on the assignments, and I'll come around and give you guys help as you need.